Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss Cauchy integral formula and Cauchy's inequality. Let's begin. If a function f of z is analytic within and on a closed curve C, and if A is any point within that of closed curve C, then at that given point the function is evaluated as f of A is equal to 1 divided by 2 pi I closed curve integration over C f of z divided by z minus 1 dz. Here we prefer a closed curve C where that function f of z is analytic. Inside that closed curve there will be a point A at which we have to evaluate the given function. How to prove that one? Let I draw a circle of radius as r, and that radius r is equal to magnitude of z minus a. It is a very small circle. Now that is converted to a closed curve C1. It is a doubly connected region. We can convert it as a simply connected region. Just taking a cross cut. So here it is a closed curve C. So a cross cut is used to convert at point A, that is the radius r, that magnitude of the radius z minus a. Now within that of region the function is analytic, and we can use the extension of Cauchy's integral theorem for multiple connected regions. How to prove that Cauchy's integral formula? You have to consider the function f of z divided by z minus a. That function is analytic at all points within that of curve C, but except z is equal to a. Which one? Which is analytic at all points within C, that is the closed curve, except z is equal to a. At z is equal to a, that function is not analytic. So what we prefer to analytic to convert that function to be analytic, we have to draw a small circle to convert that particular function to be analytic at z is equal to a, with the point A as the center and radius r is equal to magnitude of z minus a, that is, draw a small circle C1, that is circle named as C1, that is lying entirely within the curve C, within C. Now that given function is analytic throughout that of entire region, that given function is now analytic. Now the function f of z divided by z minus a is analytic in the region C and C1, that red colored regions. Hence, we can use Cauchy's integral theorem for multiple connected region. Hence, by using Cauchy's integral theorem for multiple connected region, that is, closed curve integration over C, that given function f of z minus a dz is equal to the closed curve integration that given function at the curve C1, that is the extension of Cauchy's integral theorem to multiple connected region C1, given function f of z divided by z minus a dz. Let we evaluate that particular integral. To evaluating that particular integral, we have to add and subtract f of a, f of z minus f of a plus f of a divided by z minus a dz, which is equal to integration over C1 separating f of z minus f of a divided by z minus a dz plus closed curve integration over C1 f of a divided by z minus a dz. Closed curve integration over C1 f of z minus f of a divided by z minus a dz plus f of a to that of outside, as that one is constant as we integrate with respect to dz. So f of a to outside, closed curve integration over C1 dz divided by z minus a, equation number 1. Now we have to evaluate each integral one by one. For any point within that of curve C1, first we have to evaluate the integral. Now closed curve integration over C1 f of z minus f of a divided by z minus a dz is to be evaluated. As we know, for any point C1, any point within that of C1, that is also a complex number. Let us prefer that complex number z minus a, the complex number in the form of r e to the power I theta. It is the radius r e to the power I theta, representation of polar form of a complex number. Its differentiation dz is equal to I r e to the power I theta d theta, and the limit from 0 to 2 pi within that of circle, the limit from 0 to 2 pi. Now we convert that integral to that form. Conversion: z is equal to a plus r e to the power I theta, f of a plus r e to the power I theta minus f of a divided by z minus a r e to the power I theta dz, I r e to the power I theta d theta, I r e to the power I theta d theta, limit 0 to 2 pi, r e to the power I theta, r e to the power I theta cancel out, from 0 to 2 pi, that is f of a plus r e to the power I theta minus f of a I d theta. That is one integral. Again another integral, that is closed curve integration over C1 dz divided by z minus a. So that integral convert to, in place of dz we substitute I r e to the power I theta d theta, z minus a as r e to the power I theta, r e to the power I theta, r e to the power I theta cancel out, limit from 0 to 2 pi. So I to that of outside, and the d theta integration from 0 to 2 pi. Therefore I d theta integration as theta from 0 to 2 pi, we have 2 pi I. In this way the two integrals are evaluated. Now we put the values of these integrals in equation number 1. Putting the values of integrals in RHS of equation 1, we get, that is closed curve integration over C, that given function f of z divided by z minus a dz is equal to, that is the given function, first integral value. Okay, let we solve that integral. When we put the upper limit and lower limit, means the value of r, it will be tends to 0 in place of I. When I put the limit, that value results 0. That integral is solved. So first integral value 0 plus here f of a, that integral value 2 pi I, f of a into 2 pi I, or f of a is equal to 1 divided by 2 pi I close curve integration over c f of z divided by z minus a dz. Cauchy's integral formula is proved. At the given point within that of curve at which the given function is not analytic, at that point we evaluate that given function. That value is 0 as the radius tends to 0, and we put in place of theta from upper limit and the lower limit, then the value equated to 0. These two integrals are evaluated. By putting these values, we get the result, which is known as Cauchy's integral formula. Next, Cauchy's integral formula for the derivative of an analytic function. If that function is analytic, now we treat that function is analytic within that of region, the point as we prefer. So what should be the derivative? If a function f of z is analytic in that of given region, and its derivative at that point z is equal to a of that given region R is also analytic in that of given region, that is represented as its first order differentiation f dash a, first order derivative at that given point is equal to 1 divided by 2 pi I closed curve integration over c f of z divided by z minus a square dz, where c is any closed curve within that of given region R, and that is surrounded by a point z is equal to a. Let me prove it. Very simple thing, just we have to integrate. We know from Cauchy's integral formula, Cauchy's integral formula, f of a is equal to 1 divided by 2 pi I closed curve integration over c, that function f of z divided by z minus a dz. That is equation number 1, as we already proved it. Now differentiating that equation number 1 with respect to a, differentiating equation 1 with respect to a, we get, that is its first order differentiation f dash a is equal to 1 divided by 2 pi I closed curve integration over c f of z, its differentiation del by del z, 1 divided by z minus a dz. Or f dash a is equal to 1 divided by 2 pi I, its differentiation results as closed curve integration over c f of z divided by z minus a square dz, that is f dash a. Again differentiating means it is second order differentiation. Similarly we have to calculate second order differentiation. F double dash a is equal to, here 1 into 2, that is represented as 2 factorial divided by 2 pi I closed curve integration over C f of z divided by that of denominator z minus a to the power 2 plus 1 and 2 plus 1, which is equal to 3 dz. Similarly for nth order differentiation, f nth order differentiation of that given function n factorial divided by 2 pi I closed curve integration over C f of z divided by z minus a to the power n plus 1 dz. In this way we calculate Cauchy's integral formula for derivative of a given analytic function. By using that formula we can show Cauchy's inequality. So Cauchy's inequality, if f of z is analytic within a circle, mind it, not a curve, that is a circle C, and the radius of that of given circle, here we have a circle and its radius r, which is equal to z minus a magnitude at center at O, and that function is less than equal to m, where m is any positive number. That given function, magnitude of that given function is less than equal to m on that of circle C curve. Here we represent it as circle C. So its nth order differentiation magnitude less than equal to m into n factorial divided by r to the power n, where m is a positive number, n is in the order, r is the radius. Let we prove it. Proof of Cauchy's inequality. As we already know, the nth order differentiation n factorial divided by 2 pi I closed curve integration over C f of z dz divided by z minus a to the power n plus 1, that value must less than equal to magnitude of these terms. So n factorial divided by 2 pi I closed curve integration over C magnitude of f of z magnitude of dz divided by z minus a magnitude to the power n plus 1, that value must be less than equal to its magnitude terms. Here we prefer it as a circle. Within that of circle we can use as the polar form of complex number, since z is equal to r e to the power I theta, r be the radius of that of given circle, and dz magnitude I r e to the power I theta d theta magnitude, which is equal to r d theta, and theta from 0 to 2 pi. So it is less than equal to n factorial divided by 2 pi and the given function, the magnitude of f of z divided by z minus a to the power n plus 1, we write it as m divided by r to the power n plus 1, z minus a, which is 1 is equal to r n plus 1, and the function f of z divided by I as a number, positive number m, from 0 to 2 pi r d theta, which is equal to magnitude of dz, less than equal to n factorial divided by 2 pi m divided by r to the power n plus 1. Here r 2 pi integration of theta from 0 to 2 pi, that is 2 pi. So 2 pi cancel out, less than equal to n factorial m divided by r to the power n plus 1 minus 1. So r to the power n, which is less than equal to m into n factorial divided by r to the power n. That is proved. So Cauchy's inequality is proved. So here we show Cauchy's integral formula and its proof. Cauchy's integral formula for the derivative of an analytic function, first order differentiation, second order differentiation, similarly nth order differentiation. Cauchy's inequality, providing its nth order differentiation, we show Cauchy's inequality and its proof. Now we solve some questions by using Cauchy's formula. The question, first question, evaluate the closed curve integration z square minus 3z minus I divided by z minus 2I dz, where C is a circle and equation of circle is given as z is equal to 3. Look at that given equation. Here that function, when I prefer z is equal to plus 2I, then that function is not analytic. We have to show either that point is within the circle or not. Solution: circle, first we prefer the function f of z, let f of z is equal to z square minus 3z minus I divided by z minus 2I is not analytic at point I, at point 2I, at point 2I that function is not analytic. First we have to show either that 2I within that circle or not. Equation of circle, equation of circle, magnitude of z is equal to 3. As you know, magnitude of z x square plus y square under root is equal to 3. Taking the square, x square plus y square is equal to 3 square. So x minus 0 square plus y minus 0 square, 3 square. The circle having origin, having center at origin and radius is equal to 3. Let we draw that of circle. Which one is the given curve C? 1 2 3 1 2, sorry, minus 1 minus 2 minus 3, that for x, O x dash, and y, O y dash, again 1 2, 3, minus 1, minus 2, minus 3. So the circle having radius 3. Here the given point 2i, that is imaginary axis I, that point, that for 2i. So that point 2i within that of given curve C. Now we can use Cauchy's integral formula to evaluate that particular integration. Here 2i is within the given circle, so we can use Cauchy's integral formula to evaluate that given integral. At point two I. Therefore, the closed curve integration over C here f of z divided by z minus a dz is equal to 2 pi I, that is the given function at a. Here a is equal to 2i, here a is equal to 2i. So the function closed curve integration over C, that given function is equal to z square that entirely we choose f of z, not entirely that function is f of z, we prefer only that section as f of z. So let I choose let. In that of case it is not analytic at point 2i. I use z square minus 3z minus I divided by z minus 2i dz, which is equal to 2 pi I f of a means z square minus 3z minus I at z is equal to 2i, which is equal to 2 pi I 2i square minus 3 into 2i minus I is equal to 2 pi I 4i square minus 6i minus I. It is 2 pi I minus 4, as I square is equal to minus 1 minus 4 minus 7i, which is equal to minus 8 pi I plus 14 pi. Just use the Cauchy's integral formula to evaluate that given integral. Let that function is not analytic at that given point, which is when the equation of circle, and that point within that of circle. So we can use the Cauchy's integral formula. By using Cauchy's integral formula we easily evaluate that given integral, that be the answer of that particular question. Next question, evaluate the closed curve integration over c dz divided by 2z square plus 5z minus 3, where c is the equation of an ellipse. First we have to show at which point that given function is not analytic. Here 2z square plus 5z minus 3, multiplication as minus 6, addition 5. It has two number as 3 minus that is 3 2 numbers are there, which is equal to 2 z square two 3 6, adding two numbers results 5 and multiplying two numbers as minus 6, minus 6 it results as plus 6 minus 1, adding these two numbers results plus 5z, multiplying these two numbers results minus 6 minus 3 is equal to 0, or 2z as common, z plus 6 z plus 3 minus 1 as common, z plus 3 is equal to 0. Here z plus 3 as common, 2z minus 1 is equal to 0, or z plus 3 is equal to 0, or 2z minus 1 is equal to 0. That results either z is equal to minus 3 or z is equal to half. Now we have to show either these two points are within that of given ellipse or not, which indicates the given function is not analytic at points minus 3 and half. Equation of ellipse given as x square plus 4y square is equal to 16. Now 16 divided both sides, x square by 16, 4y square by 16 is equal to 1, which implies that is x square divided by 4 square plus here 4 cancel out, so y square divided by 2 square is equal to 1. Rearranging it, x by 4 whole square plus y by 2 whole square is equal to 1. So it is the ellipse, the given ellipse, where the semi major axis 1 2 3 4, semi minor axis as 2 3 4, here 1 2 3 4, minus 1 minus 2 minus 3 minus 4, 1 2 minus 1 minus 2, semi major axis and semi minor axis. and the given ellipse according to that of equation. Look at that, here minus 3 is a point there, half is a point, plus half. These 2 points are within here minus 3 and plus half. These 2 points are within that of given ellipse. We can easily use the Cauchy's integral formula to evaluate that given integral. These 2 points are within the ellipse, so we can use Cauchy's integral formula to evaluate the given integral. Hence, the given integral closed curve integration over c dz divided by 2z square plus 5z minus 3, that is converted to two integrals as dz 2z minus 1 whole into z plus 3. Again it is represented as closed curve integration over c 1 divided by z plus 3 divided by 2z minus 1 dz plus closed curve integration over c 1 divided by 2z minus 1 divided by z plus 3 dz, just converting that integral into two definite integrals. First solving first integration and then second one. So at first integral, if in that of denominator side I prefer first integral, in denominator side I prefer 2 as common, so inside that bracket term it will be z minus half, so half closed curve integration over c 1 divided by z plus 3 divided by z minus half dz, half, that is in the form of Cauchy's integral formula. Here is the point half, that is the given function 1 divided by z plus 3, so the result will be 2 pi at that given function z plus 3. The point z is equal to half should be evaluated. Evaluating that value, 2 cancel out, pi I 1 divided by, in place of z we have half plus 3, the result will be pi I 2 divided by 1 plus 6, it is 2 pi I divided by 7. Next integral, second one. Also second integration, closed curve integration over c 1 divided by 2z minus 3 divided by z plus 3 dz. Again using Cauchy's integral formula, 2 pi I, that function 1 divided by 2z minus 3, evaluating at z is equal to minus 3, results as 2 pi I, putting minus 3 in place of z, 1 divided by 2 minus 3 minus 1, it is result as 2 pi I 1 divided by minus 7 minus 2 pi I by 7. Now putting these two equations in that given equation, therefore equation 1 becomes closed curve integration over c, the given integral dz 2z square plus 5z minus 3, first integral value 2 pi I by 7 plus second integral value minus 2 pi I by 7, it results 0. That integral evaluated as 0 from that of given ellipse. So, with the help of this video lecture, we understand the concept of Cauchy's integral formula, its proof, Cauchy integral formula for the derivative of an analytic function, Cauchy's inequality. By using its nth order derivative, we proved Cauchy's inequality. Two problems related to Cauchy's integral formula. First question solved by using the equation of circle. Second one, by using the equation of ellipse, we evaluate that given integral. The technique is, first we have to show at which point that given function is not analytic, and so if that given point either within that of equation of that curve or not. If that given point within that of curve, then we can use the Cauchy's integral formula. If not, definitely that results will be 0 by using Cauchy's integral formula, by using Cauchy's integral theorem, that results 0. If that given point within that of circle, we can evaluate that function to that point by using Cauchy's integral formula. So, with this useful and informative notes, let me wind up this session. Thank you.